Okay, so the next speaker is Sanjay Ramassamy from Kasteleyn in Paris. He's going to talk about integrable dynamics on polygons and the Dimer integrable system. Thanks a lot.
Thank you for the introduction, and thank you very much for the organizers, to the organizers for putting together this very nice program. Thank you in particular to Filippo, who is coordinating all of this. It's a great pleasure for me to be back in Florence after the previous program in 2015. And today I want to speak about both statistical mechanics and geometry with an integrability point of view. So on the one hand, in the past decades, there have been several integrable systems that have been studied in geometry that come from dynamical systems on spaces of polygons. And on the other hand, there is another class of integrable systems that has been studied in the past 10 years that are associated with bipartite Dimer models on the torus. So this last class forms a unified theory. However, the geometric dynamics are much less unified. They are more or less a zoo of examples coming either from dynamics on polygons, or there's also a very big other class of examples coming from discrete differential geometry. And the goal of my research in the past few years has been to create a framework which would generalize both the Dimer integrable systems and the geometric dynamics. And by doing so, there are two consequences. On the one hand, it would bring some unity to all these geometric integrable systems, which were previously like only examples with no particular connection one to the other. And on the other hand, what we are starting to see is that these geometric structures that we will have may be used to prove some universality results for the statistical mechanics model, for example, the Dimer model. So I will start by defining the Dimer integrable system. Then I won't give you all the examples of geometric dynamics, but just one. It will be a toy model called the pentagram map. And finally, I will define this general framework of triple crossing diagrams and explain to you how to recover the Dimer model and how to recover the pentagram map. So let's start with the Dimer integrable system. The Dimer model comes from statistical mechanics. It has been heavily studied in statistical physics since the 1960s. The setting is the following. I take planar graphs that are bipartite, meaning you can color the vertices in white and black such that each edge connects a black vertex to a white vertex. And each edge of the graph carries an edge weight, here denoted by the letters A, B, C, D, and so on. When you do probability, these edge weights are positive real numbers. But when you do integrable systems or geometry, as will be the case later in this talk, these edge weights are complex numbers. So what is the probabilistic model? Yes, please.
This restriction to bipartite graphs is something that you put on.
So yes, you in statistical physics, yes,
not necessarily.
Exactly. In general, they may be non-bipartite, but when you look at the integrable system associated with that later in the talk on the torus, it exists only for bipartite graph theory. So that's why I need this restriction for the talk. And yes, please feel free to interrupt at any time if you have questions. So we define a Dimer covering of a graph to be a subset of edges such that each vertex is exactly incident to one of the edges selected. So here the dimers are in blue, and you see that each vertex lies exactly on one blue edge. We associate to each Dimer covering a weight, which is given simply by taking the weights of the product of the weights of the dimers involved. For example, here you would have weight C times D times E. And you define a probability measure on the set of all Dimer coverings of a given graph by drawing at random one Dimer covering with probability proportional to its weight. That's a Boltzmann probability measure. What you observe is that if you pick one vertex, for example, this white vertex here, and you multiply all the weights of the edges adjacent to this vertex by some scalar lambda, then this does not change the probability measure. Why? Because each dimer covering will contain exactly one edge adjacent to this vertex. And so the weight of each dimer covering will be multiplied by the same quantity. Such a transformation is called a gauge transformation, and it doesn't change the probability measure. Since we're interested not in the edge weights, but in the probability measure that they induce, we want some coordinates on the space of edge weights modulo gauge transformations. And these are given by alternating products of edge weights around faces. What does that mean? It means that you take a face, for example, this one, you turn around it in counterclockwise order, and when you go from black to white, you put the corresponding weight in the numerator. And when you go from white to black, you put the corresponding weight in the denominator. So here you get A divided by C times F divided by D. And we have one such weight for each face, and we call these the face weights. There is an alternative definition of the face weights that I'll give you because it will be useful in the geometric context later. It's the following. It uses what I will call Kasteleyn edge weights. So right now on each edge, I have one edge weight. I am also going to add a Kasteleyn sign, attach a Kasteleyn sign to each edge. And what is a Kasteleyn sign? It's a choice of a sign that I assign to each edge, such that if you have a face of degree 0 modulo 4, then you have an odd number of minus signs. And if you have a face of degree 2 modulo 4, then you have an even number of minus signs. So here, for example, you have a face of degree 2 modulo 4, sorry, 0 modulo 4. So you have an odd number of minus signs. There's one minus sign. Same thing for this face of degree 4. And you also have the outer face, which is degree 6. So it's degree 2 modulo 4, and you have an even number of minus signs. No minus sign. So this choice of Kasteleyn sign is not unique. And what you can do once you have your edge weights and your Kasteleyn signs is to multiply them out, and you get what I define to be Kasteleyn edge weights by taking this product. And then you can express the face weights that I defined previously by the following formula. The face weight is now, if you have a face of degree 2k, it is -1 to the power k plus 1 times the alternating product of the Kasteleyn edge weights. So here it would be A divided by C times F divided by minus D, but I also have another minus sign because of this -1 in front. So these Kasteleyn signs are important because they are used to define the Kasteleyn matrix, which is an adjacency matrix of the graph. And this Kasteleyn matrix has been an important tool to compute in statistical mechanics the partition function and the correlations for the dimer model. Let me now present two local moves for the dimer model. What are local moves? Suppose you're interested in correlations for the dimer model, the probability of presence of certain edges, and you perform away from these edges a local change of the graph and also a change of the edge weights. Then these two local moves that I will define do not change the correlations away from the place where I did the move. They preserve the Boltzmann measure. The first such move is called the spider move. So if you have a quadrilateral like this in your graph, and let's say that each black vertex is attached to only one other white vertex outside of this quadrilateral, then you can erase the two black vertices, erase the 6 edges adjacent to them, and redraw a new quadrilateral like this with new edge weights given by this formula. So since I told you that we are not interested really in the edge weights, but rather in the face weights, let me tell you how the face weights evolve for this move. So you can, in particular, there are some formulas here. Note that for the weight of the central face, it just gets inverted, and the weights of the other faces get multiplied by a quantity depending on the weight of the central face. So this kind of weight changes is actually a special instance of mutation of coefficient variables in cluster algebra. That was the first move, spider move. The second local move is contraction and expansion of degree 2 vertices. Suppose you have a white vertex of degree 2, and the two edges attached to it have weight 1. Oops. Then you can delete the white vertex, delete the two edges, and contract it to a single vertex, merge the other two black vertices. When you do this operation, the face weights don't change. And I'll recombine this move into what I will call a resplit move, because that will be useful in the geometric context. You start with something like this. You first contract this degree 2 vertex, and then you uncontract it in the vertical direction. That will be a resplit move. And we use these two types of moves, spider moves and let's say resplit moves, to define some discrete time dynamics on face-weighted bipartite graphs on the torus. So you start with some bipartite graph on the torus, which has some face weights, and you apply a sequence of these moves such that you come back to the same combinatorial graph, but which will have potentially different face weights. Let me explain this on an example. But before I explain this on an example, I want to point out that it's equivalent to look at graphs on the torus or to look at infinite graphs in the plane that are periodic in two directions and whose weights, here I drew the edge weights, which you could draw also the face weight, whose weights are also periodic in two directions. Why? Because you just take one fundamental domain, which is a pattern that will repeat itself, and you can just cut this out and glue left and right sides and glue top and bottom sides, and you get a torus. So let me give you one example of such discrete time dynamics. And I will give you the example on a square grid graph. Actually, I don't want exactly the square grid. I will change a little bit, and I will apply, to begin with, this local move, which is expansion of, for degree 2 vertex here. So I change each black vertex into this, and I get this. So I will start from this graph, apply a sequence of moves, and come back to this graph. So right now, this graph carries some face weights. I want first to apply spider moves like this. To each pattern like this, I will change it into that. So I get this. Now, each time I see this, I will apply this resplit move. For example, here, you see there. What you get here is a graph that resembles a lot the graph that you had 2 slides before, but there is more different. But if you look here for the window that I chose, this white vertex on the top left is alone, and this white vertex on the bottom right is alone, but 2 slides before, it was top right and bottom left were alone. So you get the same graph, but shifted by half a unit. To get back to exactly the same graph, you need to apply again spider moves, and again resplit moves, and then you get to exactly the same, back to the same combinatorial graph, but the face weights have potentially changed. So the claim for such discrete time dynamics is that this gives rise to some integrable system. For any choice of a bipartite graph on the torus, you get like this some integrable system, in the sense, I will state it very loosely here, that it has enough conserved quantities independent, that have some particular structure with respect to a Poisson bracket that we can define. So there are some very precise results in the papers that I cited, results about Arnold-Liouville integrability, about algebro-geometric integrability. In particular, if you take the right coordinates, then the motion is translation on some high-dimensional torus. But what I do want to explain in detail is an interpretation, a relatively simple interpretation of the conserved quantities. The conserved quantities can be interpreted as partition functions for dimer covers on the torus with a prescribed homology. So first, let me remind you what the homology is. If you have a collection of directed loops on the torus, you can associate to them a pair of integers, positive or negative. And this pair of integers is called the homology. And it measures how many times the loops wind around the torus in the horizontal direction and how many times they wind around in the vertical direction. So, for example, for this loop, it winds around once in the horizontal direction, hence you have a 1 here, and it doesn't wind around in the vertical direction, so you have 0. Here it's the contrary, so you get no winding in the horizontal direction and 1 winding in the positive vertical direction. This one winds once horizontally, once vertically, so it's 1, 1. And here, both loops wind in the vertical direction, but in the negative direction. So it's 0, -2 for this one. And we use this notion of homology to define the homology of a dimer cover. So to do this, we first fix once and for all a reference dimer covering that I will draw in orange here. And you orient this reference dimer covering from the white endpoints to the black endpoints. And then if you have an arbitrary dimer covering that I will draw in blue here, and you want to know the homology of this blue dimer covering, you superimpose the blue and the orange, and you orient the blue from black to white. So what you get is a collection of directed loops, and you look at the homology of these directed loops. So here you get only one directed loop. It's contractible, it doesn't turn around the torus, so the homology here is 0, 0 for this dimer covering. For this blue dimer covering, you see that it goes up here and down here. So again, the homology is 0, 0. For this one, it goes across the torus, so you have homology horizontally, homology 1, 0. And here on this picture, I drew all the possible dimer coverings of this 2 by 2 square grid that I showed you. There are 8 of them. So I orient the blue dimers from black to white, and I superimpose my reference dimer covering. So I get collections of loops, and I can compute the homology of each dimer covering. So what you see is that these 4 dimer coverings all have homology 0, 0, and then you have 4 subsets with only 1 covering in them, and they each have a different homology. And what we do is that we look at the partition function of each subset. So we take the sum of the weights of each dimer covering inside each set. So when the set is a singleton, the partition function is just the weight of this single dimer covering. So here, for example, it's the weight of this edge, which is B, times the weight of this edge, which is C. But in this case, you have to take the sum over all 4 dimer coverings of the weights of these dimer coverings. And the claim is that the conserved quantities for the dimer integrable system are given by ratios of these partition functions. Yes?
Is that also the single coefficients of the spectrum?
Yes, exactly. So that was the dimer integrable system. Now I would like to discuss integrable geometric dynamics. And because this is a very big subject with different examples, I'll just focus on one example for simplicity. And I'll take the simplest one that I know of, which is the pentagram map. So what is the pentagram map? The pentagram map is a dynamical system on the space of n-gons. Here I'm taking the example of n equals 6, so I have a hexagon. I start at time 0 with 1 hexagon. Then what do? I draw shortest diagonals. So shortest diagonals connect vertex number I to vertex number I plus 2. And if I draw 2 consecutive shortest diagonals, they intersect at a point, and this will be one of the vertices of the new polygon at time 1. If I do this for all the shortest diagonals, then I have 6 new points. I connect them together, and I get my new polygon at time 1. So this is a map that I have, which takes one polygon and gives me another polygon. If I iterate the map, I will have the polygons for all the positive times. But then I can also take the inverse of this map and get a polygon at time -1. How do I define the inverse of this map? I take side number I and side number I plus 2, so not the next side, but 2 steps apart, and I extend them. I extend them, and I intersect them like this. And I do this for all the sides, and I get 6 new points that I connect together, and that's how I go backwards. This is the inverse map, and I get the polygon at time -1. So let me clarify something. I told you that it's about polygons in the plane. My picture was R2, the real affine plane. But actually, this dynamics takes place for n-gons, which are in CP2, complex projective plane of 2 dimensions. It was defined by Rich Schwartz in 1992. And also, you should consider these polygons up to PGL3 of C. So since maybe not all of you are very familiar with projective geometry, let me give you some reminders, refreshers on projective geometry. So I'm going to consider m-dimensional projective spaces for m at least 1. What is this? I have Cm+1, which is a vector space, and CPM, projective space of dimension n, m, is defined to be the space of all the lines in Cm+1. By lines in Cm+1, I really mean lines going through the origin. If you have a vector in Cm+1, a vector v, then it defines a line, CV, and this corresponds to a point P in projective space. The terminology here is that the vector v in Cm+1 is called a lift of the point P in CPN. And this lift is not unique. You can multiply the vector v by any scalar, and it will define the same point in projective space. By definition, a line in projective space is defined to be a plane in Cm+1. Now let me tell you about the transformations of the projective space. If you have a matrix, invertible matrix of size m+1, then such a matrix acts on the lines of Cm+1. Thus, it induces an action on CPN. The observation is that if you scale this matrix by some lambda, then this scale matrix has the same action on the lines of Cm+1. So it defines the same action on CPN. That's why the automorphisms of CPM are defined as the quotient of GLm+1 by the subgroup of scalar matrices, lambda times the identity. And we call this PGLm+1 of C. Let me also remark that if you don't have the intuition of visualizing things in CPM, you can think of an affine chart of CPM, which is given by Cm and which is dense actually inside Cm. So the picture I showed you, which was in affine space, was not too far from reality. It works exactly the same as what I showed you. As taking? Yes. Yeah, I think so. Let me define the notion of multi-ratio. Suppose you have 2 K points in CPM with the following constraint. Each even point lies on the line defined by its 2 odd neighbors. Then you can define the multi-ratio as this quantity. It's an alternating product again. P1 minus P2 divided by P2 minus P3 times P3 minus P4, and so on. Why is this well defined? Well, just look at the first ratio. P1 minus P2 divided by P2 minus P3. These 3 points lie on a line because P2 is on the line P1, P3. So on this line, you can take an affine chart and you can compute the ratio. This ratio is well defined if you have an affine chart. So if you have an affine chart, you can define this quantity, and then you may ask, is this quantity independent of the choice of the affine chart? And the answer is yes. So that's how the multi-ratio is defined. In the special case, when you have 4 points, in that case, they are all aligned, it's called cross ratio. So let me use these reminders of projective geometry to define the actual setting in which the pentagram map takes place. So I showed you initially a closed n-gon. What is a closed n-gon? You just have n points. You turn around your polygon from P1, P2, you come back to Pn, and afterwards you get back to P1. A complicated way of saying the same thing is to say that I have a bi-infinite sequence of points, so indexed by positive and negative integers, with the constraint that this bi-infinite sequence is periodic, meaning that pi plus n equals pi. So I turn around, and when I come back to Pn, afterwards I continue, and I have Pn plus 1 equals P1, and so on. So now that I have this complicated definition, it's a bi-infinite sequence which is n-periodic. I can change it slightly and replace n-periodic by n-quasi-periodic to get the definition of twisted polygon. What is a twisted polygon? If you have M, which is in PGL3 of C, then a twisted n-gon with monodromy M is defined to be a bi-infinite sequence of points, which is M quasi-periodic. Sorry, n quasi-periodic with monodromy M, meaning that when you go around from P1 to Pn, Pn plus 1 equals M applied to P1, and so on. So this is the setting in which the pentagram map is defined. It's defined on the space of twisted n-gons, and you should also consider these twisted n-gons up to the action of PGL3. So if you have one n-gon given by one sequence of points pi, if you apply some element A of PGL3 to all the points to get a sequence A times pi, I consider that the two sequences are the same thing. And because I consider only n-gons up to the action of PGL3, the monodromy M of such a twisted polygon is not well defined in itself, because if I change pi into A times pi, then it changes the monodromy M into AM A inverse. It gets conjugated. This means that the monodromy is only well defined up to conjugation. And so the results on the pentagram map are that this is again an integrable dynamics, and explicit formulas for the conserved quantities here again. And this all follows actually from the conservation of the monodromy. From the monodromy, the monodromy generates the generating function of the conserved quantities if you want. However, unlike the diamond model, these conserved quantities mostly don't have a geometric interpretation. For the diamond model, there was a nice interpretation in terms of partition functions with constraint homology. Here, there is no nice geometric interpretation in general. Another result about the pentagram map, it was proved by Max Glick, that if you look at two consecutive generations of polygons at time t and at time t plus 1, and you take certain multi-ratios of points living at these two times, then these evolve like the formulas I showed you in the diamond model, mutations of coefficient variables of cluster algebras. That was how the face weights evolved under the spider net. So now let me define a general framework. I'll define everything from scratch. And this framework will specialize on the one hand to the diamond integrable system, and on the other hand to several geometric dynamics, in particular to the pentagram map. So we introduced the setting in 2019 with Niklas Affolter, Max Glick, and Pavlo Plievsky, and we've been studying more recently the integrability aspects of the setting with Niklas Affolter and Terence George. So here is the setting. A triple crossing diagram, which I'll abbreviate to TCD, is simply a bipartite graph such that all the black vertices have degree 3. It was defined by Dylan Thurston a while ago. And then I define a TCD map as follows. It is an assignment to each white vertex of a TCD. We assign to each white vertex a point in CPM with the following constraint. If you look at a black vertex and you look at the 3 points assigned to its 3 white neighbors, then they should be aligned. The points are in CPM, I recall. So what does it mean to have 3 collinear points in CPM? By definition, it means that if you take a lift of each point in CM plus 1, these 3 lifts, which are 3 vectors in CM plus 1, they should be coplanar. which means that there exists a linear dependence relation between these three vectors. And I will use these scalar coefficients, lambda I, to attach them to each edge. So I get what I will call edge variables. These edge variables are not uniquely defined because the lifts of the points are not uniquely defined, are defined only up to scalar. So these lambda I are also not uniquely defined, they are well defined only up to gauge transformations. What are these gauge transformations? Suppose I look at one white vertex here where I have a point P1, and instead of taking the vector V1, I take V1 divided by 2. Then here I would get a coefficient 2 times lambda 1. So doing something like that would multiply by a scalar the edge variables around a white vertex. And how to get gauge at the black vertex? Associated to this black vertex, you have this relation here. And if I multiply everything by 2, I would have here 2 lambda 1, 2 lambda 2, 2 lambda 3, which would be also a valid choice of edge variables. So I would like to stress that these edge variables that I just defined, they will play the role of what I call the Kasteleyn edge weights in the dimer section. And here I realized I forgot a sentence on my slide. So I wrote the sentence here. We define the weight of a face of degree 2k to be -1 to the power k plus 1 times the alternating product of the edge variables around the face. Exactly the same definition that gave me the face weights in terms of the Kasteleyn edge weights in the dimer section. And then for this definition of face weight, you see that you have some rather simple interpretation of face weights in terms of the geometry. Why is that? It's because this alternating product of edge variables around the face is nothing but the multi-ratio of some points. So which points? Suppose you have this face here. On the face, you have some white vertices to which there are some points attached, but you also have some black vertices, and there's no point attached to the black vertices. But you replace each black vertex. So recall that the black vertices were all of degree 3. So the black vertex will have 2 white neighbors on the face and 1 white neighbor outside of the face. So you replace it by this white vertex. And so you take the multi-ratio of the following points, 1 point on the face, 1 point, which is the neighbor of the black vertex on the face, 1 point on the face, 1 point, which is a neighbor, and so on. And if you take the multi-ratio of these points and you multiply by -1 to the power k plus 1, you get the weight of a face of degree 2k. Then, just like you had for dimer models, you have 2 local moves for TCD maps. Who is gauge invariant? The alternating product of edge variables, this is a gauge invariant. For the same reason, because it's edge variables.
But again, the phase weights are going to be because they are phase invariant.
Yes. Yes. So you have 2 local moves for these TCD maps. One, which is the spider move. So here, it's exactly the same picture as for dimers, except that here, attached to each white vertex, you have a point. So what does this mean, for example, that you have this black vertex? This black vertex tells you that P1 is on the line connecting P2 to P4. And this black vertex tells you that P3 is on the same line connecting P2 to P4. So actually, when you see a picture like this, it means that the 4 points involved are on a common line. And how to change this? When you change the picture, you are just reparametrizing these points. They are still all 4 on the same line, but you will group them into triples like this, rather. So when you do such a spider move, it doesn't change the points in the TCD map, but it changes the face weights. And the way the face weights change is exactly the same formula as for the spider move for the dimer model. Now you have also the resplit move. So the resplit move is the same combinatorics as for dimers. You start with these 5 points here. So P1, P2, P3, P4, they form a quadrilateral. And this point P lies, because of this black vertex, on the line P1, P2, and also on the line P3, P4. So P1, P2 here is this side, and P3, P4 is this side. So you are extending opposite sides of the quadrilateral and intersecting them to get P. Then what is the point that you should attach to this new white vertex after doing the resplit? Well, it's just the intersection point of the other 2 pair of opposite sides of the quadrilateral. So these 6 points, P, P prime, and P1 to P4, they form what we call a complete quadrilateral. And there's a famous Menelaus theorem that gives you a relation between these 6 points. So you're probably not used to seeing Menelaus theorem written in terms of multi-ratio. Rather, you would see it using oriented length, but this is exactly a rephrasal of Menelaus theorem. And this is a linear equation in P prime, so you can determine uniquely P prime from the 5 initial points. So for this move, there's one point that changes, the geometry changes, but the phase weights don't change, just like for the diamond model. So to finish, let me explain to you how to get the pentagram map from some TCD map. So this was the picture that I showed you for, so that was a picture for a closed n-gon. I could do it for twisted n-gon, but the picture would have too many points on it. So let's just do the picture for closed n-gon, but it works for twisted n-gons. On this picture, I recall that you had 3 generations of polygons, time -1, time 0, and time 1. I give them names, P hat for time -1, P for time 0, and P prime for time 1. And then here is a portion, so it's an infinite TCD map on the plane. Here is a portion of this TCD map. Let's look, for example, at the line connecting P4 to P5. So it's a polygon, a side of the polygon at time 0. You see P4 and P5 here. Because of this black vertex, you have P6 hat on this line. And because of this black vertex, you have P4 hat on this line. So it indeed matches what we see. And I want to make an important remark on this TCD map. I do only a very short portion, but what you have here is horizontally, you have all the by infinite sequence, P1, P2, P3, and it continues in one direction, and it continues also in the negative direction. And it is the same for every line. Every line you have the by infinite sequence of points. So it is quasi-periodic in the horizontal direction because I have twisted polygons. However, it is also periodic in another direction. If you go, for example, from P3 here to there, you get the same P3. So it is periodic in this direction. So for the TCD map, for the geometry, you have periodicity in one direction. So you can glue it into a cylinder. And what you get is an infinite cylinder. And the points on this cylinder would be quasi-periodic in the horizontal direction. However, if you forget about the points, and you only look at the phase weights, the points are quasi-periodic, but the phase weights, they are periodic in 2 directions, not just in one direction. So you can, if you look only at the phase weights, glue it into a torus. That's why you will recover the setting of the diamond model on the torus, not on a cylinder. And at the same time, you would get something geometric, which is twisted, an infinite twisted geometric object. So that's my initial TCD map, and let's see how the dynamics works. So first, I am going to apply resplit to each of these vertices of degree 2. This will create new points for me, and you can check that actually you indeed get the new points of the pentagram map. For example, if you look at, say, P4, P5, P6, P1. So P1 is P7 here. It's there. So you have P6, P4, P5, P7. At time 0, you had this P6 hat, which was the intersection of P4, P5, and P7, P6. And now, after one step like this, who do you have? You have P5 prime. So taking the 4 same points, you will intersect P5, P1, or P7 with P6, P4, and you get P5 prime. So this is how really these resplit moves, they generate this, this pentagram map. So first you do resplits, and then you do spider moves, which don't change the points, but change the face weights. And you get back to the same graph with just a translation. So what we showed with Niklas Affolter and Terence George is that using this framework, we can recover the cluster variables of Glick as dimer face weights. And we also recover the conserved quantities found by Ovsienko, Schwarz, I forgot the T to Schwarz, Tabashnikov, as conserved quantities for the dimer dynamics. And to do so, what we do is that we build a general framework for twisted TCD maps living on an infinite cylinder. And the core of our work somehow is in this bullet point. So for the geometric dynamics, you get the conserved quantities from the monodromy. The monodromy will define for you a generating function of the conserved quantity. On the other hand, as mentioned by Andrea, for the dimer integrable system, the conserved quantities, the generating function of the conserved quantities are given by the spectral curve, the polynomial defining the spectral curve. And what we do is that we construct a framework in which the monodromy for the twisted TCD map can be used to define the dimer spectral curve. We have a new expression for the dimer spectral curve using this somehow monodromy matrix, and it helps us identify the two systems from an integrable systems point of view. So I must say that actually for pentagram map, a lot of things were known, so nothing is really new for the pentagram map. It's more the setting which is new. However, our initial motivation was to study something called cross-ratio dynamics. And for this, we have some new results. We show the existence of a cluster algebra structure for cross-ratio dynamics, and that is new. And we also relate the conserved quantities of that dynamics to the dimer conserved quantity. But then we realized that the framework we had created to study just cross-ratio dynamics actually applied to a very large family of systems, in particular the pentagram. So I preferred, for pedagogical reason, to run my talk on the pentagram example, because that system is a bit more complicated to explain. So, conclusion of my talk. As we saw, on the one hand, there is a unified theory for dimer integrable systems. It works for any choice of a bipartite graph on the torus. And on the other hand, we have this zoo of geometric dynamics attached to polygons, also some that you find in discrete differential geometry. And the definition of the framework of TCD maps has the benefit of putting all these geometric systems into a unified framework, just like was the case for the dimer model. And in some work that will soon appear, which is joint with Niklas Affolter and Max Glick, we define some operations on TCD maps, where we can take one TCD map living in dimension m and create a new TCD map living in dimension m-1. And this corresponds to some operations on bipartite graphs. And this helps us to find multiple cluster structures for TCD maps. In this talk, I showed you one cluster algebra structure, where the cluster variables were these multi-ratios around the face. But actually, there are many cluster algebra structures for one given TCD map. And this creates also new connections in the zoo of geometric dynamics between different objects, and some of these connections are new. And yes, and so this is one direction, using the unified theory of dimers to bring some unity to geometric integrable systems. And then there is the other direction. You can take these geometric structures that you relate to dimers and use them to try to have some some universality results for the dimer model. And this is also some ongoing work by many people around the world, in particular with the setting of T embeddings that is being developed. And so this is almost the end of my talk. I just wanted to flash this slide, which is about a very similar program that will take place in 2024 from March to June in Los Angeles at IPAM. So the title is Geometry, Statistical Mechanics, and Integrability. It's very related to the topics considered here. And here is the organizing committee. You can see that out of the 7 people, 4 have been or will be at GGI. In particular, there is Yann de Guy also as a co-organizer. And that's it for me. Thank you for your attention.
Okay, so thanks a lot. Is there a question there? Thank you.
Can you come up with a continuous version of this in the sense that, for instance, you replace the polygon by a curve and look at the motion of this curve?
Well, I know that, so speaking of continuous, on the one hand, you have Goncharoff Kenyon to study the continuous time dynamics for dimers. So this is one way to have something continuous, but to this day, it is not clear yet what is the relation between the discrete time dynamics on dimers and the continuous time dynamics. Is it just taking the continuous dynamics at time 1, time 2, and so on, or not? It is not clear yet. And in the geometric world, there are some continuous limits that have been considered for several examples. So on the one hand, for example, for pentagram map, I know that there is a paper by maybe Ovsenko, Schwarz, Tabashnikov showing that you have convergence to the Boussinesq equation. And on the other hand, so it's not really convergence results, it's more or less the other way around. People from discrete differential geometry, they started from classical continuous differential geometry and tried to discretize them. So of course, what you have is a discretization of some continuous integrable object. But then if you ask me how to do this for TCD maps, it seems hard, for example, to take the continuous limit of pentagram because I would need, I don't know how to, my bipartite graph wouldn't be a bipartite graph. It would be fields maybe living on the plane. You would have like the white field and the black field. And it's not very clear at all to me how to do something like that.
So I wasn't sure if you addressed this. Do you have, in the quiver, you seem to have always 4 valent vertices. You start with that. And can this be generalized?
So my quiver has vertices of any degree, but the mutations that we do are at vertices of degree 4. And I don't have an interpretation, a dimer interpretation of mutation at degrees other than 4, but maybe some recent work, I don't know, I've seen some papers on the archive by Casals, for example, may bring some interpretation to that in terms of fillings. I'm not sure about the answer, but maybe there exists somebody who knows the answer to such a question.
You may have mentioned that towards the end or quite quickly, but my question is, when you have this linear relation with the lambdas around the 3 vertices around the black nodes, I don't know if it is necessary to, yeah, that one. Do you know a recipe for choosing these lambdas in such a way that they define the vectors out of the black point so to have an embedding of the TCD map, which is quasi-holomorphic for what concerns quasi-holomorphicity of dimer models?
No, there are some models for which we're interested in such embeddings. For example, if you know centers of circle patterns, also called T embeddings. But for that, actually, this lives in CP1, these T embeddings. So you would embed this in CP1, and in that case, it's more or less what you are saying that we are doing. But in general, this, I mean, it was already quite hard for T embeddings. And now if you want to do this for every system, I don't know.
Essentially, you should search within the space of gauges, those lambdas which close up the polygons. It is a set of equations. Maybe you can prove abstractly the uniqueness of the solution.
But now it's polygons that live in higher dimension. Here I'm in CPM, potentially in high dimensions, right? So you would have
The lambdas are scalar.
the lambdas are scalar, right?
So, for example, if you have, sorry, I don't know, don't want to take long, but you had slightly afterwards a diagram which makes an alternating hexagon there, for example. Then you have 6 lambdas around, which are defined up to a gauge. You have to sum them up and make 0 in C, not in CPM. And this is an equation for a phase. But every phase gives you equations, and you have gauge covariances, and you have equations within the gauge freedom that you have.
Do you want to embed your graph in CPM?
No, in C.
So
lambdas are really in C, and they are the vectors from B1 to W1 in this.
But okay,
awfully.
But then you lose the interpretation as objects living in CPM, that these points were living in CPM.
But that's just, I don't know, maybe I'm completely wrong. For me, this CPM is not in the geometry. It is in the geometry of the target space.
Yes.
In the geometry of which kind of integrable system moves on the spectral lines, while the two-dimensional geometry of the fact that this is a 1 + 1 dimensional model and embeds in C is on the starting, on the physical space. So CPM is in target space, and you want quasi-holomorphicity in physical space.
Okay, so I don't know how to do this for general systems. As I said, we can do for T embeddings. Maybe we can discuss after the talk for how to generalize this.
Other questions? Okay, if not, we can thank the speaker again.